We will wrap up chapter 6. So last time we stopped at the end of the buck boost converter, and we saw that it's again we have a topology. The topology is looks similar to the other topologies from the point of view of the fact that we always have a switch and a diode, and this switch and a diode are always arranged so they're complementary. They operate in a complementary fashion, so both of them cannot be on at the same time. And there's always, at the terminals of the two switches, or I call a diode the switch, right? It's an uncontrolled switch, yeah. So at the terminals of the two switches is typically what we call a stiff voltage source. So you always find, these are the terminals of the two switches in the buck boost converter. There's a stiff voltage source here, which is a capacitor, right? It's a stiff voltage. It does not allow voltage to change quickly, right? And on the other side is a voltage source, or you can put a capacitor as well, right? So, and between the two switches is an inductor. And this is what we saw in all the converters that we saw in the previous converters, and the converters that I skipped in the chapter. They're all the same. I mean, they would be deriving again the whole voltage input-output characteristics, and then looking at the voltage ratings of the switches, and then average currents of the switches, and then the values of L's and values of C's. That's this. It's a flow. The flow is the same for all the converters. So we covered the three basic converter topologies, just because again. I mean, you can give a whole course on DC to DC converters, for example, right? But we cover the basic topologies, and then you can extract or look at the rest in an advanced course or whatever, right? We only offer one power electronics course here, but if we had offered more, basically it would be a continuation of, for example, the rest of the DC to DC converters, the rest of the rectifiers. So the switch mode rectifiers and the rest of the switch mode DC-DC power supplies, for example, and more details on the inverters that we will cover in the last two lectures. Yeah. So, but the idea is very similar, and the topology is very similar. There would always be this. Again, I like to abstract it more than just a switch and a diode case. I like to draw this. Why do I have to sign in? Serious? Okay. It's the first time it does this, but anyway. Let's see if it runs. Okay. So I like to abstract it more and use this representation of this being an arm that moves between this node and this node, where this is equivalent to a switch at the top and a switch at the bottom, and just these two terminals coming out of it, right? So two terminals on this side, two input terminals or two output, and then two input terminals or two output terminals on this side, depending on the topology that you're looking at, right? So you can have this, you can use this for the boost converter, you can use this for the buck converter, you can use this for the buck boost converter, it's the same, right? So for the buck converter, we would draw it this way. Right? For the boost converter, we would just swap the load and the source. Right? For the boost converter, we would swap the load. Here I put the source. And here I put the load. And for the buck boost converter, the way it's drawn in text, I can draw right? So this is the buck boost and the buck boost converter. All the same. all the same. Just that maybe in the buck boost they put it in a different place. I mean, they drew it differently. But I can, you can make it, you can draw it standing up and figure out a way to make it look similar, right? But at the end of the day, again, it's these two terminals always have a stiff voltage source across them. And the output terminal of this circuit that's connected to this moving pole or moving arm always has an inductor that maintains current continuous for that switching period. Here, same thing. A stiff voltage, and then this, fine, we flip the direction of current, but it doesn't really matter. What flipping the direction of current, we will go and select a different set of switches for this. Right? Remember for the chapter 1 study, we can go back to it later now. But and here it's the same, right? So this is the buck boost converter. Inductor current was in this direction, so current flows here and current flows this way. At the end of the day, these two terminals stiff voltage sources across the terminals, and an inductor in the output that maintains current continuous for the switching period. They're all the same. All power topologies will be the same. Inverters will be the same. Everything will be the same. All power converters are the same from that perspective, because their objective is to take energy from one side, right? It's always taking energy from one side and convert. It's like a transformer, right? It's a transformer that allows DC transfer. You can do AC or DC transfer with a power converter. So it's at the end of the day, you can model it like and this is what we will talk about in the next few slides. They will draw it like a pseudo transformer, and they draw something funky through it so that they indicate it's it's not really a transformer, but it's a transformer that allows you to pass DC, to convert DC as well. So all transformers, what they do is transfer power from high voltage low current to what? Low voltage high current, for example. They maintain power with some losses in the middle, but they change the condition of the voltage and current. That's what they do, and that's what the power converter does. And for the switch mode power supply to do that, it's doing that by taking energy from the source, storing it in reactive elements, taking that energy stored in a reactive element, dumping it in an output reactive element, for example. Right? That's what we saw is happening in most cases. Yeah. So so I just want to show that they're all very similar. They're all the same from that perspective. Yeah. And one thing to note here, okay? The voltage here and the voltage here, or after it's filtered, after the inductor, okay, is the same as the voltage here and the voltage here and the voltage after the inductor after it's filtered. The voltage here is the same as the voltage here or here after the voltage is filtered. Meaning what? Meaning that these switches always see a stiff voltage across them, right? They always see a stiff voltage. So these switches are seeing this VDC minus V output. It's a voltage, right? This voltage I'm chopping up with this switch moving up and down. I'm always chopping it up, taking one time connecting to the top side, one time connecting to the bottom side. Doesn't matter if this voltage is here in this case, this voltage is VDC and V output. But does it really matter? It can be VDC and 0, right? It can be VDC and 0. It can be 5 and minus 5, right? I can have a switch between, let's switching between 5 and minus 5, right? If the switch is at the top, I see 5. Switch is at the bottom, I see minus 5, right? At the end of the day, what did I'm just taking connecting the circuit to this point for a while, then connecting the circuit to this point for a while, right? At the end of the day, what I did was take this voltage, which is the difference here is 10 volts, right? So I took this voltage and I put 5 volts here for a while, and then fine, this minus 5 is my reference in this case. Minus 5 is like my 0 point in this case, right? If I'm looking at the voltage here, it's either going to be 5 or minus 5, correct? 5 or minus 5, 5 or minus 5. So what am I doing? I'm staying at 5 for a while and then minus 5 for a while, 5 for a while. The duration of staying at 5 will dictate how much positive average value I have versus negative average value I have. For example, if I stay at, for example, if this is 5 and this is -5, but I stay here for a longer period of time, what's the average value of this waveform? It's a negative number, right? Because I stayed, at -5 for a longer period of time. But can this negative number be greater than 5 or -5? It will always be between 5 and -5. Do we agree? So, and that's what's happening with the buck converter. If this is VDC, I'm taking 0 and VDC. I'm oscillating between 0 and VDC. And then the longer I stay at VDC, I get an average value here that's positive, or closer to VDC. The longer I stay at 0, I get an average value that's closer to 0. Right? Same thing with the boost converter. This output volt, in this case, it happens to be the output voltage. The output voltage here, and the relationship, its relationship to the voltage at the input, is what? Same thing. If the switch is up here for a longer period of time, then definitely I would see a larger average value here. Right? If the switch is down here for a longer period of time, then I will see a value here that is smaller. And it makes a lot of sense because remember in the boost converter, this was my switch. This was my MOSFET. I was storing energy when I was connected to the bottom here. Right? And I was able to store more energy the longer I stayed connected to the bottom. Right? That means I can live with a smaller voltage source to boost to the same voltage that I wanted to boost to, for example. Right? So here, staying at the bottom here allowed me to store more energy, even and allows me to have a high voltage here as well. Right? So, but at the end of the day, I don't care if it's a buck boost. I don't care the direction of current. I care that between these two terminals, I always have a stiff voltage that I am seeing a chopped version of here, and then an average version of that here. Same thing here. I'm seeing a voltage, a stiff voltage here. I'm seeing a chopped version of it here, average version of it here. And it's the same with all the topologies. Even inverters. We will talk about inverters in the next chapter. It's the same. The other thing that's interesting, what do you see? This current, I'll call this my pole current, right? I'll call this like a pole that's oscillating between two terminals, okay? This current here, if I have in the buck converter, my switch is up here, correct? What is the current in the switch? Remember, again, let me erase and then redraw it nicely. This is oscillating between these two nodes, right? And in the buck converter, we said we have the equivalent to this pole throw combination is this circuit. And this we said we can get from the slides from chapter 1, right? We said that, again, if this is the voltage polarity, the current polarity is this way. We go to the slide in chapter 1. Or chapter 1? Yeah, that slide here. We saw that for voltage of this polarity, current coming out of this node in this fashion, the switch is on top and the diode is on the bottom, right? So we go back here and we sort of established that the fact that the voltage here, this is V input, versus the voltage, here an average value here, here is the voltage that we see here is a chopped version of this input voltage, right? It's a V input 0, V input 0. So it's a chopped version of what I see here, right? The voltage here at this node between these 2 points is either going to be V input or 0, V input or 0, V input or 0. So its average value is always a is always between 0 and V input. It's always going to be between these two terminals, right? It's not going to be, I cannot get an average value of here of this voltage that is going to be less than 0 or higher than V input, right? It's always going to be between these 2 points here. So I always get an average value of voltage here that depends on what? Exactly. I get an average value of voltage that will depend on duty ratio. It always will be the case. This will always be the case. In any of the topologies, we agree that we represented all the topologies the same way, right? So I will always see an average value of voltage here that will depend on the duty ratio. Nice? Okay. How about current in the switch?
We decide that current in the switch would be the same as the current in the inductor when the switching period is on.
There has to, exactly. Because again, the inductor current is either going to come this way or this way, right? I mean, here it's going to come through this switch or through this diode, and they're not on at the same time. So it's going to come from this one or from this one. That means the current in the switch will always be what? Okay, the current in the switch will look like, this is the inductor current. This can be switch current, for example, right? For example, its average value will depend on what? You said it. Exactly, right? So it's the average value of this up and down waveform was IL. The portion of it that I've shaded was the switch current. The width of that will depend on the duty ratio. So I will always have switch current that is dependent on duty ratio and the current here. You agree? Always in all the circuits. In all the circuits. It's the same, right? And we will use this conclusion to draw an equivalent circuit of all these power supplies without switches. Because at the end of remember, in 420, who's taking 420 now? So in 420, again, we talked about this, that Dr. Hazem is talking about linear time invariant systems, right? You don't need to do 420 to understand to understand this course, because it's based on 214, right? In 214, you drew up circuits with independent and dependent voltage sources, and then R's, L's, and C's, right? Dependent and independent voltage sources and R, L's, and C's. With this combination of components, then you were able to come up with the Laplace equivalent circuit. Basically, you wrote the equation of the Kirchhoff voltage law using in the Laplace domain, and you came up with a Laplace domain representation of Kirchhoff voltage law for the circuit, right? And there, in that case, fine. You can, for example, you were able to relate, for example, the V input voltage to inductor current, for example. You had a relationship where you had it was Vs over V input over S, right? For a constant. What's the Laplace for a constant?
1 over S.
Yeah, so V input over S, right? So it's V input over S is here, and then you had SL here, and you had 1 over SC here, and you were able to write Kirchhoff voltage law in this S domain, right? And then from this S domain, you can remove S and put omega, right? You can convert that to the frequency domain, right? If you do that, you should be able to do what? If you convert something to a frequency domain and you have an equation between variables in the frequency domain, you can relate two variables to each other. You can, for example, write a relationship between V input over the input of S, for example, over IL of S equals, you have your equation for Kirchhoff voltage law. You can write that. This is called a transfer function, right? If you're relating two variables to each other, any two variables, you have a relationship in the Laplace domain which is the same as frequency domain, right? You can relate two variables. Any relationship between two variables, this is going to equal something. This something will depend on the circuit configuration, connections, and the components that you have in there. That's the transfer function between what? Between the input voltage and the inductor current, for example, right? And in 420, that's what you're studying. You're putting this transfer function here in these blocks. And you have some inputs and some output, right? And that's what we're doing, that's what you did at the end of 214, but you didn't relate it to 420, right? So at the end of 214, you're coming up with these Laplace domain equations for these circuits, not knowing what's the value maybe at that point, right? But the value is what you see in 420, is when you understand how to relate any two variables in a circuit in the frequency domain, you're going to come up with a block diagram or what's called a transfer. That is called a transfer function. You take that and you stick it in this box. What do you do when you stick it in this box? You know that if you give a certain V input, you will get a certain value for IL. You know that from the relationship from Kirchhoff voltage law. From Kirchhoff voltage law, you know that, right? But you've added the frequency dependence here. You've added the frequency dependence, the fact that you have L's and C's here. You've added it. It's not an average value circuit where L is short circuit, capacitor is an open circuit. You've added the time dependence of the components into the picture. So if you give V as a step, it's different than giving V as a ramp. That's what you studied. That's what you're studying in 420, right? That the impulse, if you're giving a step response to a system, is different than giving a ramp to a system, right? You will design your controller. Your system will behave differently. Since your system will behave differently to different voltage sources at the input, then you should be able to. You should design a controller to give your system the preferred response, right? So after you come up with this box, which is nothing but the Laplace domain representation of our circuit in this case. For example, between V input and IL, for example, V input of S and IL of S, right? You came up with this box. If you give a certain V input, you will get a certain inductor current. This is your Kirchhoff voltage law equation, but with the time domain dependence of the R's, L's, and C's in there as well, right? But what you're going to do in 420 is that you're going to measure this current because you want this current to be a certain value. You want this to be IL equals 5 amps. You want to charge the battery that's after the inductor. You want to do that, right? So this is what you're requiring, IL to be 5 amps. So how do you do that? You have to measure it, put a sensor in there to measure, and this sensor will also have some transfer function, right? And in 420, you're taking, okay, you have these block diagrams, and you're able to reduce, right? Dr. Hazm can give you several block diagrams, and you're able to reduce these block diagrams. They're nothing but Laplace equations. These Laplace equations are nothing but similar to equations like Kirchhoff voltage law equations, but represented in the frequency domain. So you measure that, and you bring it into a computer. In this computer, you know that your reference is 5 amps. You want 5 amps to be the inductor current at the output. The computer will, or the controller that you've designed will tell you, okay, this is what I want, but this is what I have now. I have 3 amps, for example, right? This is where I am right now. What does that mean? That means I need to give a certain input to G of S to continue increasing IL, right? And that's the controller, for example, a PID controller, right? And you will design this controller based on this transfer function and this transfer function, right? That's what you will do in 420, but this is nothing but 214, end of 214. This is where 214 ends, right? What I'm going to do now is relate what we're doing to this block. I'm going to take what we're doing and stick it in this block. Then you can go into 420 and come up with this block and this block, right? I'm not going to cover 420, but I'm just saying, trying to relate what you're going to do in 420 if you didn't do it yet, to what you did in 214 to what we're doing now, right? So we said that all our circuits will behave very similarly, meaning I will have this voltage source, the input, and I will come up with an average version of it that will be seen here all the time, regardless of the topology of the circuit. In this case, it's a buck converter, and this will be dependent on duty ratio. It's dependent on the voltage between these two terminals and the duty ratio, right? Also, we said that all our circuits will behave in the same way, and I will look at where the switch is, and it will happen to be, for the buck converter, again, I can go to my table. This is my polarity of voltage, my current polarity is this way, I can put my switch and diode. I put my switch and diode, I know it's up here, right? I know my switch is up here for the buck converter. So, current is coming this way, and current is coming this way, and the sum of these currents is equal to this IP current or IL current, right? This current will always be dependent on duty ratio. The switch current will always be duty ratio dependent on the inductor current, right? It's whenever the switch is on, inductor current will flow through the switch. It makes sense, right? Whenever the switch is on, inductor current will flow through the switch. So this is a circuit where we have switching elements. This is not something you can come up with a circuit like 214 for, right? It's not something you were used to in a 214 perspective. But after we wrote this and this, what do these look like? Related to 214 stuff. What do these look like? Forget about the rest of the circuit, but when you in your circuit in 214, you remember when you saw, two things multiplied by each other, this is dependent on something else in the circuit. What was this? What were you calling these? You had a quantity in a circuit that is dependent on another quantity in the circuit. Dependent sources. Remember the dependent sources stuff you had in 214? So this is exactly what the dependent sources stuff in 214 is. So I can redraw this. For example, I can put a dependent current source here that is D times IP. And I can put a dependent voltage source here, right? That is D times Vin. Where Vin is the voltage between these two terminals, right? So if I do that, can you do the same stuff you did in 214 now? Yes, you should. I mean, I understand. I'm not going to ask you to do it, okay? But yes, I mean, you should be able to, right? You have a voltage source here. The Laplace representation of a constant is V over S, or V input over S. This is a dependent source. The Laplace representation of that is the source value over S. This is SL. This is 1 over SC. And this is nothing but R. Right? So you can take Kirchhoff voltage law around the loop. You have one loop here, one loop here. You can have a loop here if I include the capacitor, for example, right? You can do a loop here, a loop here, and a loop here, for example, right? So you have these three equations that represent this circuit. You can combine them. You can remove variables and stick instead of for example, you know that output voltage here, the voltage over the R is equal to the voltage over the capacitor. So you should be able to do some simplifications and come up with a single equation in the Laplace domain that describes your circuit. Now, if I want to control the output voltage from in this circuit, okay, the output voltage, for example, is here, right? What is my only control variable that I have in this circuit? Duty ratio is my only controlled element, right? So now I would, you have a Laplace domain equation that's relating, V input over S, and it's relating D times IP, it's relating D times V in, it's relating SL, it's relating 1 over SC, it's relating R. Again, the objective is not to find the equation right now, or to draw, or do Laplace domain work in this course. I'm just trying to deliver a message here, trying to relate what we're doing to 420. You come up with an equation that includes all this. Now, you want to control output voltage. So what do you want to look at? You want to look at, for example, the relationship between duty ratio and the voltage across the capacitor. Or, SL, actually we're looking at inductor current. Here you're talking about inductor current. Or here you're talking about capacitor voltage. These are your the states of the circuit, right? So the states of the circuit, you're finding the voltage drop across the inductor, or the voltage drop across in Kirchhoff voltage law. You're looking at voltage drops across the components that you have. So you're looking at voltage across the inductor or voltage across the capacitor, right? And you can relate voltage across the inductor to the current across the inductor, right? And then voltage across the capacitor is typically your state as well. So if you talk about 420, Dr. Hazim uses the word state. States means nothing but variables. The variables of interest are typically going to be inductor currents and capacitor voltages and any other controlled element. The other controlled element that you have is duty ratio. So you will typically find the relationship then between duty ratio and inductor current, or duty ratio and capacitor voltage. If you do that, that's this transfer function that you have, duty ratio and inductor current, for example. You will find the relationship between them. This is your transfer function between duty ratio, input duty ratio, and inductor current, or input duty ratio and capacitor voltage, whatever you want. Sometimes if you're controlling the charging current into a battery, and this is a battery, then you want to control inductor current. If you're controlling the output voltage, if you just want to control the output voltage across the load, you're controlling the capacitor voltage, right? So which transfer function you choose, are you choosing the relation between duty ratio and inductor current, or duty ratio and capacitor voltage? That is dependent on what your circuit is trying to do, right? Are you trying to maintain current constant, or are you trying to maintain voltage constant? It's up to you, right? So the whole objective is trying to tell you that our circuit now looks like this. That's the whole objective of what I was trying to go through. That was the objective of this discussion. And if you want to include the effect of losses, because again, remember we have a diode as well here, right? If you want to include the effect of losses, we would typically include it here as a opposing voltage. So for example, remember, everything we're trying to do is convert voltages to voltage, right? I'm taking my input voltage to converting it to an output voltage. Or I'm taking in the boost converter, it's the opposite, right? Taking a lower voltage and boosting it. In the buck boost, but I'm converting voltages to each other. So to represent losses, what we did was before include the resistance of, for example, the inductor, right? I can do that. I can include that here as something that opposes. So this is my input voltage, something that opposes. It's a voltage drop. If I put a voltage drop here, I have loss. I'm considering like if it's as if I put the inductor resistor here, right? Current is flowing in this direction. I have a drop this way. I have a drop this way, right? If I have a diode here, it has a forward drop. If I include the ESR of a capacitor, I can include that, right? I can always include drops in there as well. So our textbook has a model that includes this drop. I typically don't. When I used to teach, I used to go into the control. Again, after you do this, we can go into control of the power supplies. 420 type material, but applied here, right? I don't teach that anymore within this course because many people are not taking 420 before they take this course, right? But if we did, that's what we do. That's the next step, right? You would have now come up with the Laplace equation for this, find the transfer function between the duty ratio and capacitor voltage or inductor current. That's a transfer function. Then, what is a transfer function for the sensor? Then, how do you design your controller? Since Dr. Hazm covers that, I don't, but you need to see the relationship between our circuits, our power supplies, and what he's doing. You can take this now into his class as a project, for example. Yeah. So this is for the buck converter. The boost converter is the same way, right? So we have our boost converter here. This is V output, right? How do I represent this in this equivalent circuit that we've been talking about? Again, current is flowing in this direction. What is switch current? Switch current is gonna go this way, and it will depend on duty cycle, right? It's gonna be a portion of the inductor current. When the switch is on, inductor current will flow through the switch. That's what it is, right? So this is D times IL. Same thing. The voltage here is nothing but an image of this reduced by the duty cycle of the switch, right? So it's D times V input, right? So it's, or is it 1 minus D? Because when this switch is on, remember, when this switch is on, the voltage is 0. So when the switch is off, so it's the voltage source here, the dependent voltage source would be 1 minus D times V output. So we'll have an average value of that. That's why the transfer function from voltage, the voltage transfer function for the boost converter is equating what? Is equating this average value of voltage, which is this 1 minus D times V output, to V input. That's why V output over V input for the boost converter is 1 over 1 minus D. Right? Without all the derivations that they did in the text. But that's, graphically, that's what it is. Right? But at the end of the day, I can take now my circuit and represent it as, this is my resistor, this is, what? I can put my current source here. Well, what would the value of the current source in this case be? I can put it here or here, it doesn't really matter. I can put my current source on top and maintain my voltage source in the bottom. That's fine. I can represent it the same way. What will be the value of the current source in this case? If this is D times IL, what is the current in the diode? 1 minus D times IL. And what is the voltage in the dependent voltage source? 1 minus D times V output, which is in this case the voltage across the terminals here, right? But the idea is the same. I took my circuit, which has switching elements, which are nonlinear, which are not part of what we design controllers for in 420. In 420, we design controllers for linear time invariant systems. Linear systems. Linear systems do not have switching elements. You don't switch voltage between one condition and another. Linear circuits typically change voltages or current in a continuous fashion. There's no discontinuities. Once you have discontinuities, then it's really a nonlinear system, and you have to figure out a way. If you want to use linear control, you have to figure out a way to represent it as a linear circuit. And that's our approach to represent it as a linear circuit. Is it a perfect linear circuit? No. Only a representation of it because of the fact that the input voltage is stiff. And hence the current is stiff. If the voltage is stiff, then the current at the output is also stiff. And here, because my current is stiff here, and my input voltage is also, my output voltage is stiff, so it's as if I have something that is like a box here that is changing, current and voltage at its terminals continuously, right? This is a power supply. It's a really nonlinear circuit that is doing a lot of abrupt changes of voltages and current, but that's not really what you see at the terminals. What you see at the terminals is a nice smooth version of this power conversion between voltages and currents because of the fact that you have you've properly chosen your L's and C's inside this box, right? Does it make sense? So there was one slide on this stuff, that's why I wanted to go through, spend more detail on that. So this slide is here, it's at the end, but it was a good time to cover it. And that it's called the average modeling of the switch, right? So it's average modeling of power supplies. So this is what we went through. They sometimes draw it, as I told you, it's like a transformer, but they call it a DC transformer, right? There's nothing such as a DC transformer, but a DC to converter is nothing but it's like a DC transformer. It's able to a converter can able to transform AC to AC, AC to DC. So a switching power supply is like a transformer that allows from DC to AC as well. So if you're talking about the DC to converter by itself, they call it a DC transformer. It's something like a DC transformer. So, and that's what they did here. The same thing, they put the current source, the voltage source, and then this representation of a drop. They put 0 here, 0 volts, but you can put a drop here if you want, right? And we will look at equations now for the converter with voltage drops included here. Okay, and you can do the same thing. So this is how they abstract. They took this out like that in this fashion, and anywhere they saw the switch current being a portion of the inductor current, they tied this terminal to it. Anytime they saw the average voltage being average representation of the voltage at the terminals, they put this terminal there. So for the buck converter, they put it in this fashion. For the boost converter, they put it in this fashion. For the buck boost converter, they put it in this fashion. Remember the AP? AP is where the terminals here are seeing that stiff voltage, whose average value is represented by this voltage source, right? So in the buck converter, my AP was here. In the buck boost converter, remember my two switches were on top, so my AP was on top. My AP is on top. In the boost converter, we swapped the voltage source of the input and the output, right? So my AP was here, but it's flipped, I think, PA here. Just draw these three terminals in place of these C, P, and A, and go through the discussion that I went through. Okay? Basically, what they did was, whenever they see the switch current, or the switch current, depending on the inductor current, they put C. So C for the buck converter was somewhere here, right? Here. This is IC, this is inductor current. C was the inductor current. So C is the inductor current for the buck converter here. C is here for the boost converter. Right? This is nothing but the buck converter, the inductor current. And these two are the terminals across which you see the full voltage, whose average value is represented by this voltage source. Do you see what I'm saying? Yes? Yeah.
Boost configuration, that C, P, and A.
Yeah.
I don't get how when CA is connected, the current direction in the dependent source would be.
No, boost for the boost converter. This is your source.
Yeah.
Current's going this way, right? Current is going this way, and the voltage, the output voltage is here, right? The output voltage is here. So what voltage do you see? Okay, let's redraw it. C, P, and A. C, P, and A here, right? That's what they did. Let's see. And A is the dependent current source, and P is the dependent voltage source. Okay? C, forget about C. A is the dependent current source. And P is the dependent voltage source. The way we drew it was and this was what my switch, this was my diode, this was my switch. Okay, so what is the current in the, this is what, this was what your, this was A? Yeah. The current here is what? If this is a switch, this is a diode. They drew it in a funky fashion, actually. I don't like the way they drew it, honestly, but let's see what they did, yeah. Here's what they said, that this is D times the IC, which is this. This is IC, correct? And then this is D times VP, D times VAP, D times VAP, D times VAP, which is this voltage. This is VAP. This is D times VAP. I don't like the way they do it. I can look at it, but I would just, I mean, I would do it the way I did it, honestly. I would look at it again, but the way I did it was, I think it makes more sense. If you look at what I did, this was my switch, this was my diode. This is inductor current, right? This is switch current. This is diode current. Switch current is always going to be D times, switch current is always going to be D times IL. It's always going to be D times IL. The switch will always be like that. And the diode current will, in this case, will always be 1 minus D times IL, right? And if this is my output voltage, then the voltage here will always be what? For the boost converter, this would be 1 minus D times V output. Why? Because when the switch is on, the voltage is 0. Right? When the switch is on, the voltage is 0. When the switch is off, the voltage is what? It's V output. Right? So when the switch is off, the voltage across these 2 points is equal to V output. Right? So I can now represent this in this fashion. I can put my current source here, and this current source would have a value of 1 minus D times IL. And I can put my voltage source here, and it will be represented as equal to 1 minus D times V output. And this would be your V output. For some reason they flip it in the text. They have this as a voltage source, and they have this as a current source. Right? If you look at what they have in the text, right, between the inductor, so this inductor current, so they call this terminal C, right? In the boost converter, they call this terminal C, right? And they call this P and this A. And they call this P, and they call this A. And then between, so at A there's the current source, and then at P is the voltage source, right? So at A is the current source. At A is the current source. I flipped that. Because I think this makes sense. I think what they're saying doesn't make sense. Again, the objective is really to have you hopefully make sense out of it. I mean, it's not about memorizing the C, P, and A. Okay, the idea is to be able to tell me, show me this. Yes? No? Try it for the buck boost and buck boost converters. I mean, we did it for the buck and the boost. The buck boost, I mean, it will be very similar. So we have our voltage source here, right? We have a switch here, we have a diode here, we have the inductor here, and this is my output, correct? So current is flowing this way, current is flowing this way. What is inductor current? Is IL. Switch current is D times IL. Diode current will be 1 minus D times IL, right? That's I diode. That's I switch, right? And the voltage across this node, these two terminals, is what? Is V input, actually plus V output, because V output is negative, right? So it's V input plus V output, because V output is negative in this case. So it's V input minus V output across these two terminals, but V output is negative, so V input plus V output. So this voltage here this is V input here, and then minus V output here. So the voltage difference between them is V input plus V output, yeah. So what is the voltage that you see here? When the switch is closed, we were seeing what voltage across the inductor? V input, right? Because the diode is open. When the switch is closed, diode is open. What?
So the switch is 0 voltage.
When the switch is closed, what's the voltage across the inductor? It's what? V input. When the switch is open, what's the voltage across the inductor? V output, right? So we were seeing V input, V output across the inductor here, right? So this, remember what I was saying? This switch here is selecting between the voltages at these two terminals, right? And here we saw that it's V input and V output. So what's going to be the voltage here? It's V input and negative V output. V input, negative V output. V input, negative V output. So it will have an average value where? That we will see here between these two nodes. Not between these two nodes. This waveform will have an average value equal to what? Average value of this waveform, right? This waveform, depending if the duty cycle, if you stay at the positive, at V input for a longer period of time, then you will have an average positive value. If you stay at the V output for a longer period of time, it will have an average negative value, right? So how would I represent this circuit then? You remember, this is where we said the average. This is the voltage waveform that you see here. The waveform that you see here is either V input or minus V output. Here, when the switch is closed, I see V input here. Okay. So how do I represent this? Plus minus D V input minus V output. So V input minus V output. So D V input plus V output. Remember, I am between these 2 points. Right, so I have a differential voltage that is V input, at its peak value is V input, its minimum value is V output, with a negative value. So I'm always going to be between, I'm always going to be less than V input and less than V output, yeah, between the two nodes. Does it make sense or not? No? Or V input minus V output? What is it? If V output I take as this way, it's V input minus V output. If I flip V output, it's V input plus V output. Depends on the polarity here. So if I go with the polarity in the text, if I go with the polarity in the text that they've used to derive the buck boost converter, they do what? They keep this polarity as positive. They keep this polarity as positive so that the voltage across the inductor is one time V input and one time V output. They don't, it's V input and one time V output. And then they show that they're opposite in polarity. Right? So if I do that, so if the voltage here is V input minus, then the voltage across these two switches is V input minus V output according to this polarity. According to the polarity that they've chosen here, the voltage between this point and this point is V input minus V output. Okay? So I would draw this as, I would write this V input minus V output. D times V input minus V output. Yes, no? And this current is diode current will be 1 minus D times inductor current. Yes? No? We drew it for all three, so draw them again for all three. Okay, so draw them again for all three, and whenever you see the diode, put the dependent current source. So for the buck converter, we had our switch here, we had a diode here. For the buck converter, actually, we put the voltage, we put the current source here, right? So we did this D times IL, and this was, the current was what? This is the voltage. This was D times V input. D times V input, and this was my inductor, this was my capacitor, this was my resistor, this was my source. Right? So this current was flowing through here. This current is a part of this. Okay? This current is a portion of this. What portion? The portion that depends on the duty cycle, because this is the switch. If this was a diode, it would have been 1 minus D times IL. But because it's a switch, it's D times IL. Right? And then the voltage across here. When this diode is on, the voltage is 0. Right? When is this diode on? In the 1 minus D time. Right? When is it off? Off is when I see a voltage. When is it off? When the switch is on. When the switch is on, when does that happen? During the duty ratio, during the on time of the switch. So during the on time of the switch, I'm seeing a voltage equal to V input. Right? During the off time, I'm seeing 0. Right? During the on time, I'm seeing the voltage V input. So I'm only seeing a portion of the voltage that is proportional to the time that the switch is on. That's why this is D times V input. And this is D times IL. Okay? For the boost converter, our MOSFET was here. Diode was here. This is IL. And this is V output. When the switch is on, I'm seeing 0 volts here. And when the switch is off, I'm seeing a voltage equal to V output. So when is the switch off? During the 1 minus D period. So during the 1 minus D period, I'm seeing the voltage V output appear. That's why if you replace this by the voltage source, you get 1 minus D times V output as the equivalent value for the voltage source that you replace here. And for the current source, what is my diode current? This is my inductor current IL. When the switch is on, it's seeing D times IL. So when do you see current in the diode? When the switch is on or when the switch is off? When the switch is off. When is the switch off? For 1 minus d times, for the 1 minus d period. So 1 minus d times IL is the switch, is the diode current, right? So if I draw this way, I draw this as a dependent current source equal to 1 minus d times IL. This would be my load. This would be this would be my voltage source. The voltage source value would be 1 minus d times V output, where V output is this output voltage here, and this is my input. Okay? Yes? And for the buck boost, we have our switch here, diode here. This is IL. Diode current is, what's the average value of diode current from with respect to inductor current and duty ratio of the switch? Exactly, it's 1 minus d times IL. How about switch current average value? D times IL, right? That's the average value of switch current. IS, this is average value of switch current, average value of diode current. Then the voltage across these two terminals, if this is V input and this is V output, then the voltage across these two terminals is V input minus V output. So I can redraw my circuit this way. D times V in minus V out. Okay?
Do we always replace the diode with the transfer?
No, in the buck converter, no, right? Does it make sense or no? Basically, I mean, this is how you would solve for average currents in the circuit as well. So if I ask you now to size, okay, select switches for the buck boost converter, how would you go about that? You would have to know this, and you would have to know this. Do you agree or not? Because remember, how do you select switches? Peak voltage and average current, right? Peak voltage and average current. Average current is this. These are the average currents in the diode, average current in the switch. Do you agree? Okay, so I'll try to make sense of what they have, the block they have in the textbook, and share that with you next time. But for now, let's try to finish up the rest of the chapter. But at least you got that idea. The idea is that the fact that we can take our circuit now and transfer it to a linear time domain circuit, a linear circuit where we can write Laplace equations for and apply 420 materials to, right? What you will need from all of this is to make sure that you understand how to calculate the average currents through the switches in all circuits, right? Because that is how you will size up select your switches, right? So you select switches based on peak voltage and average current. Peak voltages is, okay, have the switch open and look at the voltage across the switch. For the buck converter, it's going to be V input. For the boost converter, it's going to be V output. For the buck boost converter, I think it's going to be V input minus V output. Okay. The other topic we want to address a little bit here is, okay, if you have a certain load current that you would like to achieve that has a certain amount of ripple, you will design your inductor for that ripple content, right? How do you design an inductor? We said we look at the voltage waveform across the inductor. The area under that is the flux linkage that we're storing the energy in the form of flux linkage around the inductor. That area under the voltage curve, if it decreases, I'm able to choose a smaller inductor. If it increases, I would require a larger inductor, right? So what if I would like a certain amount of ripple going to my load, right? But instead of using a very large inductor, I put two of these circuits in parallel. Right? This is interleaved operation, meaning, okay, this is a buck converter, and this is a similar one in parallel, right? This is the same reference point, but this is a similar one in parallel. This inductor can have a large amount of ripple. This inductor can have a large amount of ripple. What is happening at this node? The sum of these two currents are summing up into and flowing into your load, correct? That's what's flowing into your load here. The sum of these two currents. If I make the inductor currents here phase shifted with respect to each other, right? So they both have large ripple, but they're phase shifted with respect to each other. I can do that, right? You can operate this switch a little bit after this switch, for example, right? If you do that, what happens? These two inductors have a certain value of ripple that they are designed for, right? You have a certain voltage because you have a certain input voltage, certain output voltage, the same. So your voltage across the inductor will not change, right? So voltage across the inductor will not change. Switching frequency will not change. So how do you expect to change the ripple, right? We cannot change the ripple. If I have the same voltage transfer ratio, meaning the same duty ratio, and I have the same value of inductor, then I have a fixed ripple, unless I do something like this. If I shift the inductor currents with respect to each other, right, by half a switching period, for example, then what happens? Then if I add them up, the sum will have less ripple, right? It's like, remember what we did for the rectifier, the 12 pulse rectifiers and 18 pulse rectifier? It's the same. So the sum here is going to follow the shape with less ripple. Right, so you're able to produce less ripple with same size inductors. So instead of buying a large inductor, you live with two smaller inductors. Is it good or is it bad? I don't know. So it depends on your design, right? So if you require such a low ripple and you don't have enough space for a large inductor, but you maybe have space for two smaller inductors. Maybe you do, maybe you don't. It depends on your circuit design. That's one way to achieve this, something like that. So that's something I wanted to point out. And you can do that for all the converters. So the basic idea is to have the inductor current sum up. So inductor current the inductor current output coming in from two inductors. So you can do that for the buck converter. You can do that for the boost converter. You can do that for the buck boost converter. You can do that for all the switching power supply topologies if you wish. It's like putting power supplies in parallel. Right? At the end of the day, it's the same idea. The idea is putting power supplies in parallel, but phase shifting the waveform so that it makes something useful for you. You don't need to phase shift the waveforms, right? Because if you add the average value of current from supply 1 plus the average value of current from supply 2, it will be the average value of current that you require, right? At the end of the day, you require an average value of current because you have a DC-DC converter. You're looking at the average value of the current that's output. So at the end of the day, you can get the same average value. If you don't phase shift them, you get the same average value but with the same large ripple. So why not phase shift them and get less ripple for no cost? That's what this is saying, right? So the discussion on switching loss, I think I will have to wrap up next time. So then, what we did was we looked at all the converter topologies. We looked at how to select switches for all the inductor topologies. You select switches based on peak voltage across the switch and average current, right? And then we selected inductors and capacitors. So we selected the circuit requirements of inductance and capacitance, and then we looked at how to select real inductors and capacitances. Right? Real capacitances, we looked at ESR, the effect of ESR and how it will change the value of capacitor that you select. Real inductors, we looked at effect of, the real inductor would have a resistor in series, for example. What is its effects on what is the effect on efficiency, for example? We sort of looked at that. But how do you select a real inductor? We didn't really do too much of that. How did we say we select real capacitors? We said that we select real capacitors based on breakdown voltage, maximum voltage, because that's how the voltage with the dielectric will break down, as well as the ripple current, because that's what's causing heat in the inductor. How do you select the real the capacitor? Sorry. How do you select the real inductor? Something that relates to heat and something relates to physical phenomena. What? No. Something that relates to the physical phenomena was the maximum flux that you can push in a core, right? Imax, right? The maximum current that you can push in there. And then something that relates to the heat that's being produced, it's the I squared, the RMS current that's flowing through the inductor times the resistance of the inductor, right? So we have 4 components we're selecting in all the topologies. The switches, the switch, a diode, and then capacitor and inductor. Switch diode is peak voltage, average current, both. Capacitor is peak voltage, RMS current ripples, I squared R still. Inductor is peak current or maximum current and I squared R as well, right? So both inductor and capacitor is I squared R because the capacitor has an ESR resistance. Inductor has the series inductor of the widening, right? So both of these are what's contributing to heat. Then we have a physical phenomenon in the inductance. It's peak current, maximum current, because that limits the amount of flux you can push through a core. And the capacitance, it's the peak voltage, because that's where the dielectric will break down at, right? So that's how you select all 4 components without considering switching loss. So next class, we'll wrap up this chapter by considering switching loss.